It's a great privilege for me to introduce our colloquium speaker today, Shep Doeleman, who serves as the director of the Event Horizon Telescope. And he started, I remember him in the trenches, when was it, 20 years ago? Well, almost 20 years ago. Basically starting to advocate for this project. Shep finished his undergraduate studies at Reed, right, College, 1986. Then he went to a postdoc and eventually to Haystack at MIT, where he was an assistant director. And then we were able to attract him to the Center for Astrophysics. I take a little bit of the credit because we worked together back then. We started working with Avery Broderick and others on our vision for what you will hear later. And Shep, without Shep, this project would not come to fruition. That's clear. It's by now a collaboration of over 200 people. 200. Yeah, and the leadership is here, and that's clear from, for example, if you see the video that Peter Gallison produced on the project, you will see the white walls of the Black Hole Initiative, which was established in 2016, about a year before the data was taken that will be discussed today. And so we're very proud of this baby that came out of the womb of the Black Hole Initiative. There is now a culture of people working on black holes here at Harvard University, both coming from different disciplines, mathematics, astronomy, physics, history of science, and philosophy. And the Event Horizon Telescope was very much at the focus of the Black Hole Initiative, and we are very proud of the accomplishments of the EHT under the leadership of Shep. And of course, all of you saw the image that came out on April 10th. It appeared on all the major newspapers above the fold, which is non-trivial for a scientific discovery. Not many science items are featured there. And it illustrates the importance of an image and how much more exciting it is for the public to recognize that we are looking at a black hole versus recognize that we confirm the existence of the Higgs boson, which you can't really see. So there is something special about the visual impression, and Shep sort of saw that 2 decades ago and made it happen, and we are all grateful for that. Shep.
Okay, thanks very much. Can everybody hear me? Yeah, so Avi left one thing out of the introduction. Between Reed College and coming to MIT as a grad student, I did spend a year in Antarctica. It's not for everybody, but it helped develop this nice obsessive quality about my personality that helps when you're trying to steer 200 people to a common goal. And it also gave me an appreciation for doing science in crazy circumstances. And that's where we find ourselves sometimes in the Event Horizon Telescope. To look at the most extreme objects, we sometimes have to go to the most extreme places on the planet. And so it's very helpful to have that under your belt. So I am going to talk about this project, the Event Horizon Telescope, today. It's kind of been a labor of love for many people. The idea is that humans can turn the Earth into a telescope, and we can see one of the most mysterious objects in the universe. Maybe the most mysterious object in the universe, if you don't count the human brain. To do this has required a huge technological development and also a theoretical development, and scientists working across borders around the world. And if we can do this, and we can open up a new window onto the theory of general relativity in the one place in the universe where it might break down, the edge of a black hole. So it's been a very exciting ride. I know there have been a few talks about this here, so this will be my particular take on it, and I'll walk you through this adventure we've had. So the first, I'm gonna set the stage by looking at Hercules A. It's a galaxy, quite a distance from the Earth, and you see this little smudge here, all the optical light from stars. But when you look at it in the radio, you see this extraordinary light speed jet emanating from the very center of this galaxy. This is about 1.5 million light years across. It's huge. It pierces the entire galaxy. The only thing we think that can be powering that is a spinning supermassive black hole that weighs billions of times what our sun does. And so the object of the HT is to look inside there and to see what's powering this radio jet, and also what's powering this X-ray flux that's also around the active galactic nuclei. So something is powering the centers of these galaxies. What is it? And can we really zoom in on it to take its measure in a geometric sense? So, maybe I'm too far away from this thing. Oh, there. So let's talk about M87, which is the galaxy where we actually made these observations. This is a Hubble Space Telescope image, and you see here what Curtis saw in 1918, a little bar shooting out from the center of this galaxy. He didn't know what it was, but he knew it was odd. And the distance here is about 10,000 light years, so it's a little bit smaller than that first example I showed you. In the first example, Hercules A, that's the equivalent of about 20 billion supernovae going off over about 1 million years at the center of that galaxy. Here, this is about the equivalent of 1 supernovae a year. Still pretty energetic by Earth standards and Milky Way standards. Now, if you rotate this just to get a better perspective and you zoom in on this, and you overlay it with what you see in the radio. That was an optical image. Now we're looking at the radio. And you see they overlay perfectly here. And this is at 20 centimeter wavelengths with the Very Large Array in New Mexico. And you drop that away, and you see, again, this very, very well collimated jet of material coming out of the center of the galaxy. And what's more, you see these telltale signs of where the jet is running into the galactic medium. These are shock waves here. And you see one over here. So right away you know there's probably another jet coming at the other side. And the reason we don't see that is because it's moving away from us. And just as a train whistle gets higher in pitch when it's coming towards you, we see this forward-coming jet because it's Doppler boosted towards us, because when material is moving near the speed of light, all the emission from it gets beamed in the direction of it, that it's moving. And everything here is invisible to us because it's moving away from us. Okay, so there are really two jets, and we're looking down the barrel of this jet with M87. And there's been a whole cottage industry now of zooming into the center of this galaxy because it's one of the few where we can get very good angular and linear resolution. It's one of the best objects to study if you want to know how these jets are launched. So here we go in at smaller wavelengths, so higher resolution. Now we're about 1,000 light years, and we zoom in yet again to 500 light years. We see that same jet there, and then we move in again. Now we're 12 light years. We're 12 light years across here. Let me go back a little bit. And we see this well-collimated jet at all scales. And here we are at 4 light years across. Now we're zooming in just to the very heart of that galaxy. And when you go in even more, if this will cooperate, you wind up coming into 0.3 light years in the center here. This is the best image that we have ever made of the center of this galaxy. This is really state of the art. And yet we can't see what's happening in the center there. Okay? The point of the Event Horizon Telescope is to find out what's happening. If we could zoom in by another factor of 10 or so, what is happening in the center of this galaxy? Now, people have been thinking about this for a long time. And I'll show you some slides that back that up. But really what we think we would see is something called the black hole silhouette or shadow. When you illuminate a black hole with a lot of hot gas that surrounds it, and of course the gas is very hot because it's all trying to get into a very small space, so it heats up to 10 billion degrees or so. So think of a three-dimensional flashlight illuminating the entire space-time around this black hole. You see that the diameter of this should be about the square root of 27 times a handful of constants, or the Schwarzschild radius, which depends only on the mass. And that's if it's not spinning. If it's spinning rapidly, then you'd expect it to be 4.5 times the Schwarzschild radius. So we're trying to build this Earth-sized telescope to see this feature. It's the hardest way you can possibly imagine to calculate the square root of 27. I'd recommend you use a calculator instead of doing something like this. But we will be able to get the square root of 27 out of this measurement. And of course, the shadow size and shape encodes all of GR, so we might hope to make some tests of general relativity if we could measure that. Lay a ruler across space-time to measure a prediction that Einstein made 100 years ago. And of course, it was made 100 years ago, so David Hilbert, just a year after Einstein came up with his theory of general relativity, found that term, 3 times root 3, as the impact parameter of light around a black hole. And so did Max von Laue, not to be outdone. And then this is an animation that shows really the strong bending of light around the black hole. So the black hole is shown here in the red, and we'll see photon paths doing full loop-de-loops around this black hole. This is not weak lensing. This is lensing of the strongest caliber, of the strongest sort. And when you get a bunch of photons moving around that black hole, as you would with this hot gas that surrounds the singularity, you wind up seeing at a distant screen, which is a stand-in for us here on Earth, this ring. This is the last photon orbit. All men who saw this, our jaws hit the floor. This was a moment when nature was so kind to us that it presented this image, this really clear signature that we really had a right to hope for, but no hope to expect. Okay? You got to think about this. This is a really cosmic coincidence. An eclipse happens because the moon happens to be just the right size to occult the sun, and the distances just happen to work out so that the moon just moves in front of the sun, and you see the corona. It blocks all the light. Here, the Earth turns into a telescope, as you'll see. It just is able to resolve this black hole. Everything works out very nicely, and nature gave us this. Oop, is it working now?
Yeah.
Okay. So to put this in perspective, and to tell you that we're just overjoyed that XKCD gave us a couple of comics, you can see here that Voyager would fit well within here. So we're looking at about 3.5 times the size of our solar system. And inside that are 6.5 billion solar masses. Okay? Now to put this in perspective, the best case we've had to this point for a supermassive black hole are orbits of stars around the 4 million solar mass black hole in the center of our galaxy. And those stars come within 1,400 Schwarzschild radii. This is now coming within about 1.5 Schwarzschild radii. So we zoomed in our ability to test these predictions of GR by about a factor of 1,000. Now, how did we do it? The rest of the talk is going to be spent about telling you how we did it, how we verified our results, and where we're going in the future. So we use this technique called Very Long Baseline Interferometry. And for those of you who are not familiar with it, we basically turn the Earth into a telescope by taking radio telescopes at opposite sides of the Earth, looking at the same black hole at the same time. And then we time tag all of that data with hydrogen maser clocks, atomic clocks, which lose only about 1 second every 10 million years. And that's so that when we can compare the waveforms at the different telescopes and align them perfectly without having them jitter back and forth, which would ruin the correlation. Now, when you do this, and you bring all the disks back together, you record them on hard disk drives, because of course you can't beat the bandwidth of a 747 filled with hard disk drives. Okay? Even if I take some of these modules and walk across the stage here, I'd be faster than the fastest internet on the planet. And when we correlate those, when we compare those together, we wind up creating a data set that has an angular resolution as though we had a telescope as large as the distance between these radio dishes across the Earth. It's a standard technique, but what the Event Horizon Telescope did was to put it on steroids and take it to the shortest wavelength possible, testing our ability to create low noise electronics and high speed recording so that we could pull this off. Now, it's not just getting 2 telescopes, but you have to fill in this Earth-sized virtual lens. And so we do that by letting the Earth rotate underneath of us. And you see here, each one of these points corresponds to an antenna pair, as you just saw in the earlier slide. And each of those swing through an ellipse on this plane. And this is essentially a representation of the Earth-sized virtual lens. So over the course of an evening, we fill in all the spaces of this virtual mirror. Now, we don't fill them in perfectly, and that will come into play a little bit later, but we fill them in enough that we can make an image of what's on the sky. Now, we started off, as Avi said, I don't know, 5,000 years ago, maybe 20 years ago. Seems like 5,000 years ago, honestly. And we made an experiment on this particular source in 2009, in which we looked at a short baseline here between California and Arizona, and 2 long baselines to Hawaii. And this was the source as we knew it at the time. And what I'm showing you here is a plot of correlated flux density versus baseline length. So as you move out on this side here, you're getting higher and higher angular resolution. Now, if the source has a finite size, you would expect that as you go to longer and longer baselines, you start excluding some of the flux. You'd expect lower and lower flux if there's a finite size to this black hole. And of course, that's exactly what we saw. We see a lot of flux density here, a lot of energy at short baselines, and on long baselines, it was diminished. So we measured a size of this of about 40 micro arc seconds. That's basically equivalent to being able to read the date on a quarter in Los Angeles from Boston. So it's some of the highest angular resolution ever carried out from the surface of our planet. But we didn't really know whether this was a ring or a blob. If it was a ring, it would have come down here and bounced upward, as you'll see later. If it was just a blob that had no real structure to it, it would have gone down as you see here. So the problem was we were not able to get long enough baselines to test this region right in here. And that's what we wanted to do with the Event Horizon Telescope and build out the entire array. Oop. Okay, so we did that. And this is the array that we attempted to field. Calibration games, and you can dig out detections where you didn't think you could dig out detections because you have such a large aperture. And so to do this, we had a completely separate international effort. You can see a fruit salad of logos here. And what we did was we found out, we installed a system so we could phase up all those antennas perfectly and make one recording on one system in Chile. And what you see here is that before you turn on the system, all the phases across this array are essentially random, but as soon as you turn on the system, everything cinches up to within 9 degrees. So we get greater than 95% efficiency of merging all these 60 dishes together. What happens when that occurs is you get so much sensitivity, you can play a very interesting game. Okay, so if you look at a triplet of baselines with ALMA at one vertex of the triangle and 2 weaker dishes at the other vertices, then you can phase stabilize the entire array. So you see here ALMA to Mexico and ALMA to Arizona. You see in red here these phase excursions due to turbulence in the atmosphere. So you can't trust the phase of these measurements at all. But when you subtract those out, you wind up being able to integrate for long periods of time on the SMT and LMT baseline, Mexico to Arizona, and you essentially get a phase-stable system. So you go from being able to integrate from just a short amount of time before the phase changes too much to being able to integrate for minutes on end because you have that very strong baseline always to ALMA. And that is what changed the game for us. All of a sudden, we could look for faint detections to smaller dishes over long periods of time. And that allowed us to fill out the entire UV plane or all the baselines to get the kind of resolution we needed to make images. Wow. There we go. So over 3 years, we built out the entire array. This is the thing that I think many of us are most proud of. So you see here the LMT in Mexico, and this is Gisela Ortiz, one of the graduate students tending to the atomic clock there. We also went to the Apex telescope just near ALMA as a completely separate element of the array, and we got detections there. The South Pole telescope, of course, that was a really heavy lift, really run by the University of Chicago and University of Arizona. And then we had the IRAM 30 meter here, which was in Spain, and we got detections there. So throughout all of those, that was 3 years of concerted effort to outfit all of those telescopes with new instrumentation. And this is the new instrumentation that we developed for the entire project. We revolutionized how very long baseline interferometry was done by capturing data at an unprecedented rate. So up until this point, we'd been recording, let's say, 1 gigabit per second, 2 gigabits per second. To pull this off, we ramped up to 64 gigabits per second. Okay? And to give you an idea of how impressive that is, don't take my word for it, this is Moore's law. Right, so all the gaming software you have, all of the chips in your supercomputers and so forth, they track this curve here, and we managed to track that curve over 20 years. Okay, so we hitched our wagon to 13-year-old gamers and commodity disks and things like that and CPUs. And in so doing, we created an instrument that we could never have really conceived of 20 years ago. And this equipment here has been shipped to all different sites around the world. So what happened in 2017? Well, we got tremendously lucky. Okay? We got a lot of time on some of the most sensitive telescopes in the world. We had an 8-station array that I just showed you. And over 10 days, we triggered 5 nights of observing. Okay, why 5 nights over 10 days? Because we needed contingency against weather. Sometimes it's perfectly acceptable weather above the site you're in, but then at Alma it's snowing and we simply can't run. Okay, so it's a heartbreaker, but you have to swallow it and you go on. We recorded at 32 gigabits per second. The weather happened to be fantastic. It was one of those situations where day after day, we kept getting good weather. And we would make the decision, well, are we going to run or not? And it was yes, and we were all dead tired, but we did it anyway. And it was really a wonderful experience, except for being tired all the time. And it all worked. We had detections to all 8 participating telescopes. This is the virtual lens we were able to put together. So almost at every site we could have gotten a detection, we dug out a detection. We optimally filled this virtual plane to optimize our chances to make this image. Now this is the first inkling we had that there was something really tremendous in the data. Okay, so what you're seeing here is the first part of that curve I showed you before. This is the flux of the source versus baseline. Up to this point, we had never really gone beyond these points here. But all of a sudden, we found that bounce that I steered your attention to before. And that is a telltale signature of some azimuthal symmetry, some ring-like feature. Possibly a disk, but really a ring. And then this second bounce here clinched it, right? The fact that it comes up and down again and bounces. This is the signature of a ring. And I think all of the people in the collaboration remember where they were when they first saw this, right? And there were a lot of smiles and a couple of high fives. But this is what showed us immediately that we had something. The reason we think it's a ring and not a disk at this point is because a filled disk would have this null all the way over here. So that's how we began to think that we were looking at a ring and not a filled disk. So then the whole collaboration came together and tried to make sense of this from an imaging standpoint. How do we make images? And most importantly, how do we assess human bias? How do we prevent ourselves from seeing shadows everywhere? As the saying goes, to a child with a hammer, everything looks like a nail. Okay, so if you've got a shadow detector, everything starts to look like a shadow, right? So we split up into 4 teams, and this has been described, I think, even in this room before. Different regions, different methods all came together, and they worked in isolation for 7 weeks on these data. Okay, so they did not talk, we didn't cross-fertilize, everybody did their own thing. And the reason we do this, as I like to say, is because it's very difficult to tell the difference between labradoodles and fried chicken. Okay, you think you know what you're looking at, and you can get into a room and you can convince everyone that you're looking at a labradoodle, but it's really fried chicken. And of course, it's even harder when you look at chihuahuas and blueberry muffins, right? So, I mean, it's a little funny. I know we're all laughing, but there's real human bias here. You can get into groupthink when you're all in the same room, all looking at the same data, all using the same algorithms. And so you really want to be able to tell the difference between foodstuffs and domesticated animals. Okay, so we all came together July 4th, and we revealed for the first time all of these different teams. 2 of them used regularized maximum likelihood methods, which are different than the traditional clean algorithms. This is a deconvolution algorithm. This is a forward propagating method that uses a maximum entropy algorithms. But the idea is that different algorithms were used, different teams, and they got the same ring-like structure. Now we knew we were onto something. And this was a happy affair. This is some of us together. I want to stress again that this was a collaborative effort. There were an equal number of people, I think, on telecons that were cheering along with us when we saw these kinds of images. So it was really a collectively uplifting moment for the whole collaboration. Now, then we spent a long time trying to make this go away. This is all credit goes to the imaging teams who did this. They formulated a strategy, and they carried out this strategy of purposeful tension, really trying to make this image go away. And they did it by looking at some fiducial shapes, some fiducial images, like a double and a filled disk, an asymmetric ring and a symmetric ring, all of which had the same kind of shape, the same bounces when you looked at it in that flux density versus baseline length frame that could mimic a ring. Okay, and they did that, and they reconstructed everything using all the different algorithms, and they tuned all of the algorithms so that they got a double when they wanted to get a double, a disk when they wanted to get a disk, asymmetric ring, and symmetric ring. Everything was tuned to give us exactly what we knew was going in with simulated data. And then they sicked them on the real data again, and we got, with 3 different algorithms, these images. Okay, so then we knew finally that we had imaged this light ring around the event horizon. Now, we also knew that we had confidence in all of the algorithms because we didn't just look at M87 or Messier 87. We also looked at 3C279, a different quasar, completely different object, completely different part of the sky. And we saw a totally different structure, but again, the same structure across all of these images. Here's the core where the black hole is in this object, but you also see this elongated jet to the south. We also looked at different days. As I told you, we observed this over 4 days. The whole campaign was 5 days. We only observed M87 for 4 days. You can see that in each case, we get this ring. They're slightly different, and there are ongoing studies right now to determine how variable they are. Are we seeing rotation around the black hole as a function of time? It turns out that the light crossing time of this black hole, GM over C cubed, is about 9 hours. And the time it takes for things to move around the black hole is between 3 days and a month. So we need to have a little bit more time than 4 days to adequately and statistically significantly see things move around the black hole. But that's something for the next set of observations that we do. This is a very nice animation that was put together by Daniel Palumbo, Maciek Wielgus, and Michael Johnson, which shows the power of getting new sites. So if you only have 2 sites here, Mexico and Arizona, you can only tell roughly how big the emission is around the black hole. And when you add another site in Alma, you can tell that it's even smaller, and you begin to see a little structure here. But it's really when you add the outrigger in Hawaii that you begin to see this ring-like structure here. And when you add the telescope in Spain, that's when you get the full ring. So in VLBI, as with real estate, it's location, location, location. So as I'll tell you later, we plan to build out the array even more to sharpen our focus, and it's all about where you put those dishes next. Another way to see it here is as the Earth rotates, you'll see the virtual aperture fill in, and all the data show up here. And these are the 3 different methods that we described before. And when these bars are flashing, that's when the observations are being made. This is a very nice animation, again, by the same core group of people here. So you can see that over time, you start to fill in this telltale curve. Some of these start to come into focus before others. Little blobs shift around. It's not exactly sure which features are abundantly reliable, abundantly robust, but the fact that we have this ring is kind of without question. So then we asked, well, what does it mean? So, what does it mean from the standpoint of these accretion disks around black holes? And by the way, this is going to be seizure-inducing. Okay, so we went through and looked at about 60,000 different simulations. We looked at spin, we looked at the ratio of temperatures of different particles, we looked at different kinds of magnetic fluxes, and we created a whole library just to interrogate the data that we had. And the reason is we want to be able to figure out which way the black hole is moving, which way the accretion flow around the black hole is moving, and there are basically 4 different combinations. So the black hole can be spinning in one direction, it can be spinning in the other direction, and you can have the accretion flow moving with the black hole spin or against the black hole spin, so so-called prograde or retrograde. Okay? So in this case, the black hole is moving in the sense of the black arrow, and the accretion flow is moving in the sense of the blue arrow. So here it's retrograde, and here it's prograde. Here it's retrograde, and here it's prograde. And only in 2 of these cases do you get that telltale brightening at the bottom. And that's because, remember, you're looking down the barrel of this thing. So you think of it as the spin is pointing into the page, and the light speed gas is moving up from under the black hole. That's brighter in that direction, and we see that. And so it's only these 2 cases that we can possibly have. The black hole is always moving in this direction, so the black hole spin is always pointing into the screen. And the way this, and you might think to yourself, well, wait a minute, if it's a retrograde orbit and the accretion flow is moving in the opposite direction of the spin, why wouldn't that explain also that brightening in the bottom? And that's because if you look at the, this then shows you what we're looking at here. So this is the jet coming out towards us. This is the accretion flow around like that. But these 2 movies kind of show you what's happening in the prograde sense and the retrograde sense. So in the retrograde sense, you can see here the spin is moving in this direction close to the black hole. And in yellow, you see the accretion flow. And that's moving in the opposite direction. But always the gas close to the black hole, which is responsible for that glow in the south, is moving with the spin. So even when the accretion flow, this is important, even when the accretion flow is moving in the opposite direction, the gas close to the black hole is still moving, is co-rotating with the black hole. And the same thing happens in prograde, of course. The black hole is spinning this way, and the larger scale accretion flow is moving around that way. So it always is dependent on black hole spin. And that's important because one of the basic models for how these black holes launch jets is something called the Blandford-Znayak effect, where magnetic fields are anchored into the horizon of the black hole, and they're spun up, and charged particles, which are constrained to move on those magnetic field lines, are flung out like beads on a wire from the north and south poles. And that's what we're seeing here. We're seeing the black hole govern the genesis of that jet by rotating magnetic fields very, very close into it. Now, we don't exactly know where the emission is coming from. We thought that we'd be able to figure out exactly where all the photons were coming from around this accretion flow and this jet launching region. But it turns out that if you have a magnetically arrested disk, so a magnetic field stopping the accretion flow from coming in, or whether you have a standard normal evolution disk where you have turbulent magnetic fields all the way into the event horizon, you can get it in the funnel wall here. This is the direction to the Earth here. The funnel wall goes out this way in the jet. Or you can have it in the midplane. Many different models fit. So there's still a lot of work to be done to figure out how this works in the prograde case and also in the retrograde case. So in either case, you can get things to give you the kind of emission that we saw, and you can't really pin down where it's coming from. So there's a whole another set of inquiries that we have to make with future observations. So now let's get into geometric modeling. This was a very interesting exercise. Some of it was led here at the Smithsonian and CFA, and some of it was led at Perimeter Institute. But the idea was, how do we fit this, and then how do we measure the mass? Because we should be able to measure the mass of this object. So this is an animation put together by Dom Pesci, who was one of the postdocs here. And you can see that you can make a pretty easy to understand geometric model. You carve out the center, you shift this over, it rotates, and then you blur this. And you can get, with just a few, several parameters, between 11 and 13 parameters, a pretty good description of what we saw. Okay? And then this is an animation also that Dom put together showing that you go through this entire zoo of models, and we have enough computational power and enough good data that we can start to really measure the histograms and the posteriors of some of these things we want to fit for. And so in this case, you're looking at the orientation of this versus the diameter, and you can measure basically the diameter right off of this. So this was a big effort that was part of how we measured the size and the mass of this black hole. Now, the problem is you can measure this size of the ring, but how does that relate to the actual photon orbit? Okay, the photon orbit is this collection of constants, mass, and Newton's gravitational constant, and so forth. And we know, putting into a model, exactly what that ring should be, exactly what the size of that ring should be. But remember, from the first simulation I showed you, there are wisps everywhere. There are some wisps on the outside, wisps on the inside. So how do you know what you're actually looking at? We solved this. and I'm showing that here, the shadow diameter gives you this equation I showed you before in terms of angular diameter. It's some number, the square root of 27 if it's a Schwarzschild black hole, times 2 times the angular diameter measured on the sky. And generally what this means is that the angular diameter is equal to some constant times that angular extent. Now that number alpha would be exactly 10.4 in the Schwarzschild case, and if it was the Kerr case, the maximally spinning black hole, it would be 9.6. But nature is not that kind to us, it's messy, so we have to empirically figure out what that constant of proportionality is. And we did this by generating many, many GR-MHD simulations, all 60,000 of those that I was talking to you about. We generated synthetic data, and by putting in empirically determined errors, because we knew what the receivers looked like, we knew the decoherence of the atmosphere, we folded all that in, made noisy data sets. And then we made those geometric fits that I just showed you. We extracted the angular diameter, and then we compared with the known quantity that went into the GR-MHD simulations. So we knew what went in, we knew what we measured, and we were able to empirically calibrate this. And at the end of this, we got an answer of about 6.4 billion solar masses for the size of the black hole. And this shows a couple of details that happened as part of this. So the first stage in part 1, we took 3 fiducial images, and we just changed the kind of errors we put in. Okay, so we said, well, we know that the receivers have these certain qualities, and so we'll change the kind of errors that go into it. That made almost no difference here. What did make a big difference was looking at all the different spins, all the different magnetic fields, all the different temperature ratios of the fiducial parameters that went into the GR-MHD simulations. They still gave us a pretty constant value here, but this determined the basic scatter. The basic scatter in our mass estimate comes from the fact that we don't really know which of the GR-MHD models is appropriate. So we averaged over all of them. We basically marginalized over all of these different GR-MHD simulations. And we got this fairly good and robust mass. Now we can do the same thing in a completely different way. So we can take those lovely images that we made, and we can measure the size of that ring just with an edge finding algorithm. And this again is a lovely animation put together also by Dom. And you can see that you move this radius around the image, and you can measure the width of the ring and also the location of the ring. And this gives you a direct measurement with an uncertainty of the diameter of this ring. Okay? Completely different way of doing it. Okay? And we wind up doing the same kind of thing. We measure that constant proportionality. It's a little bit different this time, but we get essentially the same mass, 6.5 billion solar masses, completely different method of measuring this ring. And you can see that across all different days with different algorithms, we get essentially the same kind of the gravitational radius here multiplied by this gives you 6.5 billion solar masses. Just think for a minute. I know I said a lot of words, but really what we did was we laid a ruler across the photon orbit of a black hole and measured its mass. Okay? That's never been done before. And the reason this was important is because there were 2 separate mass estimates in the literature. There was one that came from dispersion of stellar velocities around the center of M87, and that gave us about 6.5 billion solar masses. And there was another one that looked at gas dynamics, the motion of gas around the center of the galaxy, and that gave us about half of this mass. Okay, so in the model fitting method and the image domain feature extraction, you need a third one, which I'm not going to go into. All of these gave us a mass that matched the stellar dispersion mass. They were completely non-consistent with this gas dynamics. The reason for that is because gas operates a little bit differently than stars. Stars truly are point sources that trace, in almost a Newtonian sense, the gravitational potential of a black hole. And gas can suffer from shocks or pressure support, so you don't quite know how it will move around a black hole. So that might be understood. Or maybe it may be that we just need a better calibration of this method. But this method seems to hold in the case of M87, and that has ramifications for the masses of other galaxies that use this same method. So where are we going over the next 3 years? Everywhere. Right? So we want to have new stations. Again, location, location, location. So we're adding Kitt Peak in Arizona, Noema in France, and we hope to add many small dishes around the array over the coming years. And that's really important because up to this point we've used existing dishes. The magic of the EHT is that we took a bunch of facilities that were not meant to do this work, and we tied them together with a network of atomic clocks, and we created an entirely new instrument, but we only worked with what we had. This is probably the best scientific value for the dollar. Gotta be careful here. Ever. Okay? All right. I could be wrong, but I'm willing to argue that over a beer or something stronger later. The fact that we were able to make an Earth-sized telescope lever billions of dollars of existing infrastructure just by putting together innovative pieces of equipment at each of those sites to make them work in tandem, that was something I think very remarkable. But we want to add new dishes at specifically tailored places around the world to optimally now fill in that Earth-sized virtual lens. That will be the work of the next decade. We also want to move to the cloud correlation. It turns out that the computational requirements for processing all this data goes as n squared. Okay, so we're looking at pairs of antennas. So the number of pairs is n times n minus 1 over 2. So as we start adding 6 or 8 or 9 more dishes, you're really putting pressure on these correlation facilities that merge the data together. So we want to shift to the cloud where you can have virtually unlimited processing power. And then we want to go to higher frequencies because higher frequencies, of course, give you better angular resolution. And the ring is, of course, achromatic. So we should see the same ring at higher frequencies as we do at lower frequencies. Dynamical imaging is a possibility to make true movies, both time-lapse and real-time of black holes. And of course, we want to go to longer baselines. We are not intrinsically limited to the surface of the Earth. And I'll show you that in a moment. Okay, so if we add many, many dishes around the Earth, we shift from these black points you see, which show us what we had in 2017. We add all these red points with the extra dishes, and then if we go to 345 gigahertz, we then get the blue. So you can see there's a transformational change in the filling of this Earth-sized virtual lens when we go to higher frequencies and put many more dishes around the world. And that has direct impact on what we can do in terms of science. So this is what we had. This is a simulation of the field of view that we've been looking at so far. And if we had many, many dishes after 2025, we'd be able not only to see the black hole here, as you see here in this inset, we'd be able to tie it directly to the jet itself. And that's what we're missing right now. That's why we don't know where these photons are coming from for the black hole, as I said before. But if we could make this connection, we'd be able to solve that problem. Really solve jet genesis for the first time. See how these black holes generate these outflows that redistribute matter and energy on galactic scales right where it happens. And this is some wonderful work really pioneered by Michael Johnson and Katie Bowman. Michael was, I think, one of the first postdocs we had here in the EHT group, and Katie Bowman is another postdoc going off to be faculty at Caltech in June. And they have pioneered these methods of dynamic regularization or making movies out of sparse data. So this is what we might be able to do with what we have now, possibly extending beyond the standard imaging techniques to make movies. But if we had many, many sites, we'd be able to reconstruct very, very detailed movies of this spiral structure moving around the black hole. The reason this is important is because the light bending around the black hole is one test of Einstein's theory of general relativity, but the motions of matter, which can't move at the speed of light, are a completely different test. If we could measure the periods of orbits around the black hole, that's a completely separate test of general relativity. Now, we'd also like to go to space, not just because it's cool, not just because there's a little bit more money in it, but also because you immediately start to fill in the Earth-sized virtual telescope on an hourly basis rather than a daily basis. So what you see here is at 345, all the magenta lines show you what we can do at 345 now, because not all of our sites can go up to that high frequency. Okay? But if we had a single large telescope in orbit, this is what we would get during the course of many, many hours. And that lets us go from this simulated image here. This is what we could do with just the magenta lines. And this is what we can do with all of those. So at 345, we get an extremely crisp image of the black hole, seeing some of the spiral structure here. And of course, if we went farther from the Earth, we'd be able to sharpen that focus even more by making larger than Earth baseline diameters, increasing the size of our fundamental telescope. I hasten to add that Daniel Palumbo, one of our new graduate students in the EHG, is really leading a lot of this effort. And he has a paper coming out very, very shortly on some of this, on some of these space techniques. This gives you a better idea of viscerally what that means to go into space. This lumbering filling in of the UV plane over here, the human palette gets pretty sophisticated pretty quickly, right? So this used to be amazing, and now it's just ho-hum. This is what you can do with 4 low Earth orbiters. You get a completely filled aperture. You can do the best imaging possible with this kind of filling factor. Okay, so where do we stand? We've made some remarkable progress. As Avi said, I've been working on this for a long time. VLBI is the epitome of delayed gratification. You take the data, you capture it, you've got to bring it back to a central facility, you've got to wait for 6 months for the South Pole to defrost, then you can get into the South Pole, you bring those in, you finish your correlation. So we're used to waiting for a long time. 20 years is really pushing it, but it's all been worth it. So in this time, we made robust images of the photon orbit in the shadow. That morphology from all those GRMHG simulations I showed you is perfectly consistent with the Kerr black hole in Einstein's GR, and we hope to test that a little bit better. The basic limits on our test of GR right now are the fact that we don't know the distance. Galileo first looked through the telescope. It wasn't the end of astronomy, it was the beginning of astronomy. We're looking at the first images, and they're just going to get better and better over time. And I think this is really a new era in astronomy and even physics writ large. I want to emphasize this is a global and team effort. We started small. We had about 20 people going to the tops of mountains and making these observations when it was not really known that we would succeed. But now we have 200 people, and that's enabled us to get time on all these telescopes, diversify our portfolio, and collect resources from around the globe. To build a global telescope like this, you really need a global team. This is an incomplete group of some of our local team here. I've never been happier to work with this crew of people. It has been a real pleasure. When I first got into this, I thought, oh, when we get the image, that's going to be the thing. And over time, I've realized that it's really the people that make this happen. A person next to me said, well, we need computers, and we need some more telescopes, and we could use some electronics. And I just had to hit my talk button, even though it wasn't my chance to talk. And I said, we need people. We need really smart people who are willing to invest in this. That's what moves this forward. And actually, would you mind everybody just raising your hand if you're on the team here at SAO? It's a really wonderful group to work with, and we couldn't ask for a better host institution. Smithsonian, the Black Hole Initiative, as Avi said, the Center for Astrophysics. It's really been wonderful. I can't think of this happening in too many other places. This then is a kind of obligatory slide, but also a wonderful slide showing all of the stakeholders that form the board. These are the affiliates all around the globe, many institutes, about 60 institutes. And then it's no wonder you may have seen this before. We estimate that 4.5 billion people saw this image within the first week of it coming out. And it happened because of websites, it happened because of European Southern Observatory website with illustrative images, the NSF website, but mostly people could not get enough of it. I did this taxi test or an Uber test. Every time I went into an Uber, I'd say, have you seen this black hole image? And 100% of the people said, oh yeah, I know exactly what you're talking about. And a couple of them tried to explain it to me. You know? And I just said, that's amazing. How do they do that? And they're just like, oh, God, do I have to do it? Do I really have to go into detail with you? I said, yes, yes, I would love for you to tell me more about how this works. So that's my take on this story. It's been a wild ride. There's more to come. Thank you for your attention.
So we have time for questions. Go ahead, Marion.
Once you have telescopes in space, are you planning to fly a 747 there to retrieve the data?
Oh, that's a great question. As a matter of fact, at 1:30 this afternoon, we had a strategy session about what we might do in space and how we might study that and explore it a little bit more. It turns out that either we can have high-speed recorders on there and capture the data and then over time bleed it down with traditional telemetry, or there's this new generation of laser communication, free space optical techniques that can reach 1 or even 200 gigabits per second. And I think that over the course of the next decade, that technology is going to catch up to our needs. And that's ultimately what we'll wind up using.
We need the Moore's law now in a different context of communication.
Yeah, we need more Moore's law.
Yeah. Please.
It's a question on the image. There is a feature at a lower level of brightness, about 50 degrees northeast. Is that being residual or it might be real? It appears in 3 of the images at least.
I mean, the brightening on the south.
No. It's
At an angle, at the bottom, bottom right.
30 degrees from the north or east. You see there is a faint structure.
Which one are you talking about?
That's outside, larger scale.
This one.
No,
All the way out.
Oh, you mean out here?
to the corner, left corner.
This one.
That appears in several of the images. And
Yeah.
the questions before. That will mean
I,
or there is a real
Yeah.
possibility.
Yeah, everything out here, let me just say, everything out here we probably don't believe is probably an imaging artifact. And so we've tried to understand the variance in these maps, what to believe and what not to believe by running many, many simulations. And the stuff all out here in these 4 corners, while it may appear in some of the images, is probably not believable. But we'll know more next year because we're adding some of the sites that would give us more of a handle on what's happening on large scales. So when we add Kitt Peak, for example, that will give us a short baseline between the SMT in Arizona and Kitt Peak of only 160 kilometers. That will give us a better idea of what the large scale flux is doing and pin that down. So as I said, this is just going to get better. So stay tuned. But it's a great question. That's the question to be asking.
More questions up there?
Congratulations. You must have started this when you were 12 years old.
Stop.
But yeah, as you're looking back into what 55 million years ago into Einstein's brain here, do you have any other sense of an application for this, in addition to or beyond?
Well, that's interesting. That's interesting. So there are a few astronomical contexts in which this would be useful. So for example, outside of evolved stars and star-forming regions, there are what we call astronomical masers. So there are stimulated emission regions that are powered by a star that will tell you how the star's atmosphere is breathing in and out. And they're small enough and bright enough that they could be imaged with the Event Horizon Telescope. So there's a whole different branch of astronomy that we could apply this technique to. But thinking more broadly and channeling something that Katie Bauman, who I don't think is here, told Congress the other day, the kinds of imaging techniques that we're employing here, trying to use sparse data to see moving things, that's the kind of thing you might look to medical imaging for, right? So you think of the heart beating inside the human body and having an MRI of that with just a few sensors around it. So you have a sparsely sampled data set and something's moving in real time. So it could be that these kinds of techniques will also feed into that, and that we might learn something from those techniques too. So there's a broader context to think about these results in.
But one never knows with blue sky science how far it will take you in the future. I mean, nobody expected Einstein's theory of gravity to be useful for GPS. Yeah.
Yeah.
Martin, you had a question?
Yes. If you go to 5 or 10 times the baseline, and you can image a bunch more black holes, these will be in different higher accretion states, most of them. So I don't know, have you looked at the feasibility of the surface brightnesses going to be high enough?
Well, that's a great question. So the first part of your question is, yes, there may be a few sources that come into range for horizon scale resolution. The first one is a Sombrero galaxy, M104, right? So that'd be the next one. Cygnus A is also a very, very bright source that we might hope to resolve maybe partially the event horizon, although that's much smaller. It remains to be seen to what surface brightness we can get down to. I think with the techniques that I showed you using ALMA as the core and then looking at the smaller dishes, we think we can get down to 6-meter dishes and put those around the globe and get down to the Millijansky level, right? So if that tells you where we're headed. And I think as we expand in bandwidth too, because remember, the higher frequency you go, the fractional bandwidths are still huge. We just have an untapped vein of signal-to-noise ratio that we can access just by going higher in bandwidth.
Question, Charles?
So 6-meter dishes would sound inexpensive relatively speaking. Do you need a major clock to reach lumetri? At what point does the cost of the clock become redundant out of the equation?
It never does. Yeah, the hydrogen masers are about $300,000 right now, and even the smallest viable dish, 4 or 5 meters, that has a very, very smooth surface to go up to 345 gigahertz, probably you're talking at least $1 or $2 million at the smallest level. So we're looking at about a 10% perturbation. But even there, we're looking at ways to stabilize quartz oscillators and condition them either over the internet or with free space optical that would allow us not to require hydrogen masers, these atomic clocks, but to use, $20,000 crystals that are slaved with a phase lock loop to a farm of masers somewhere else that they receive information from via satellite. And by the way, that's, I'm not sure who asked before, but that's what we want to use for space.
Yeah.
So we could fly a refrigerator-sized maser, or we could fly a crystal and simply condition it from the surface of the planet.
It's amazing. This watch is as precise as any watch built in the history of humans, because it uses other clocks. And so the same principle, using clocks elsewhere and communicating the information.
So we will send you to the South Pole. Be careful, Avi. Don't, stop bragging about your watch, or you may find yourself on an airplane.
There was another question over there. Erwin?
Just curious, what was the best explanation you got when you pressed these random people for explaining the
Oh, well, actually, I never asked them to explain it. They would just spontaneously start explaining it, and then they would be impatient with me because I was not catching on quickly enough. I think the people that explained it to me said, they turned the Earth into a telescope. I think that's really what captured people. I think the most interesting thing and the most unforeseen element of this whole enterprise was the extent to which it resonated with people. And I think it did that for a couple of reasons. One, this was something that we've been told is invisible, just by the definition of it, and we saw it. We turned the Earth into a telescope, despite all the things that divide us in humanity. We all got together and made it work. And the cosmic coincidence of the Earth being just the right size, in a Goldilocks sense, to see this black hole that's 55 million light years away, that happens to be the right mass, that happens to glow in the part of the radio spectrum where photons can free stream from the deep gravity well all the way to us to show us this photon ring. It's kind of hard to make that up. But I think people were touched by it.
And probably in Congress they thought about who to send into a black hole from the other party.
Well, one party wants the other party to go in, and the other.
Yes, go ahead.
Does the orientation of the jet matter to the ability to do this
Oh, that's a really interesting point. So we're looking down the barrel of this jet. So everything is, you expect everything to be pretty circularly symmetric. If we were looking at it edge-on, as we might the center of our own galaxy, because we're in the plane of the galaxy, so it makes sense that we might be looking at it edge-on. So we would expect really in the case of Sagittarius A star in our galaxy to see a crescent, and that might be a little more difficult to see. Imagine if one side of that is very, very bright and the other side is dim, you might just get this elongated feature, so it remains to be seen. But in this case, we had enough of the ring because it was symmetric, because it was coming at us without too much Doppler boosting, that we were able to complete that arc. So I think in that sense, looking down the orientation that we had probably worked in our favor.
Last question in the back.
So for all of this to work, you need really, really good weather. Like, what is the likelihood? Did anyone actually calculate for, I guess, like during proposal season or whatever? What is the likelihood of having all the weather synced up in good observing conditions? And like, is there actually any problem with when you're adding more and more baselines? Does that become more and more of an issue?
Yes, so it's a wonderful question. We actually started to tackle this, and we have some people working on that within the group, but maybe some of them are here. The idea is, how do you employ game theory to figure out when to trigger a night, given the kind of weather conditions you have, given historical weather? And it turns out that we kind of expect to lose maybe 2 sites per night. So even on days when we might trigger. So the 5 days out of 10 that we trigger, maybe some of those will have most of the sites, but not all the sites. Oddly, as you add more dishes, it gets a lot easier. Because right now, we're kind of on the edge, so losing 1 dish, 2 dishes, we're in the soup, right? It's difficult to recover from that. If we had 20 dishes, well, we could lose some percentage of them, but still have enough to do all the science we want to do. So the answer is more.
But the likelihood of 5 out of 10 didn't make you religious.
No. Okay. It turns out we have looked at this, and we have a likelihood function, and it turns out that we're okay now, but with many more dishes, it would not be so much of an issue.
Well, let's thank Shep again.
Thank you, Avi.